Hello, welcome back to the second course in physics. And in this lecture, we will be talking about another element of circuit analysis, circuits that are relevant to circuit analysis. Another parameter, which is the inductance. And we will be defining the inductance, and we will be talking about inductors, which is relevant to the circuits, electrical circuits, and the desired behavior that we will be talking in the next few lectures. This lecture will contain a general introduction, and then we will define the inductance. We will define the self-inductance. Then we will evaluate the self-inductance of a long solenoid depending on that definition. We will also consider the toroid, and we will evaluate the self-inductance of a toroid. And then we will introduce the concept of the mutual inductance. We will consider two coaxial solenoids and evaluate the mutual inductance for them. And then we will derive the energy in a magnetic field. To start talking about the inductance, this concept is linked. This concept is linked to the flux change in a circuit and to the induced electromotive force, or to the induced current in the circuit. So an induced electromotive force in one circuit can be produced by, for example, changing the current in the circuit itself. Since a circuit carrying current will have a magnetic induction arising from that current. So if we change the current in the circuit, we will be changing the magnetic induction, and thus the magnetic flux across that circuit as a consequence of changing its own current. So this is one way of producing electromotive force inside the in the circuit by changing its own current. Or we can change the magnetic flux and thus induce an electromotive force in a circuit by varying the current in another circuit that is nearby. So if we have a loop and we have another loop sitting in the region of that loop, and if we vary the current in this loop, this current variation will introduce variation in the magnetic flux, and that variation in the magnetic flux will cause changes in the magnetic flux across this circuit, and will induce an electromotive force and will induce current in that circuit. So these are ways of inducing electromotive force in a given circuit. And thus we notice that there is a relation between the linking flux across a given circuit and the current that produces this linking flux. So the relation between the linking flux and the current of the same circuit, this relation involves a geometrical factor, as we will see in the near future. In a little while, it will include a geometrical factor, a factor that depends on the geometry of the system, of the circuits, the geometrical factor for the circuit itself, and this geometrical factor is known as the self-inductance. So this is the geometrical factor that appears in the relation between the linking flux and the current of the circuit itself, self-inductance. And now the linking flux that can be arising from the effect of a current in another circuit, a nearby circuit, a second circuit. The relation between the linking flux in one circuit and the current of the other circuit involves also a geometrical factor for the two circuits now. And this geometrical factor is known as the mutual inductance. And in our discussion, we will be defining these, and we will be deriving these factors for the different geometries, for some selected simple geometries. Now we talk about the self-inductance. The relation between the flux and the current in a circuit is given by this linear relation. The flux in a circuit is related to the current by this relation, and this is the proportionality factor. L is the proportionality factor here. So this is a loop. It has an electromotive force, and this electromotive force drives a current in the loop, and that current produces a magnetic field. The magnetic field itself that is arising from this current crosses the surface area of the loop, introducing a magnetic flux that is flowing across the surface of the loop. L, this factor L, that is the proportionality factor between the current and the flux across the loop, is the self-inductance. And this self-inductance, as we mentioned a little while ago, depends on the geometry of the circuit, as we will see also in special cases to be discussed in a little while ago, in a little while from now. The unit of self-inductance in the international system of units is called Henry. This unit is, from the definition, has a unit of flux, magnetic flux, which is the Weber, divided by the unit of ampere, of current, which is the ampere. So Henry, H, capital H, is equal to Weber divided by ampere. And thus, this defines the unit of inductance in the international system, and it is defined as follows. A circuit has a self-inductance that is equal to 1 Henry if a current of 1 ampere produces a flux of 1 Weber turn in that circuit. And we use here Weber turn in order to, because we have to always take into consideration the number of turns, the number of turns or loops in the circuit that we are taking into consideration. Like, for example, if the circuit consists of only 1 turn, then the flux is equal to this B times the area of that 1 turn. If the circuit consists of 2 turns, then the flux is twice as much as the flux in 1 turn. So we always have the flux in terms of Weber turn. We have to take the number of loops which makes up the circuit into consideration in calculating the flux. Now, a change in the current flowing in the circuit produces an electromotive force according to Faraday's law, and the direction of that induced current follows from Lenz's law. It opposes the effect, and this can be evaluated from Faraday's law and Lenz's law. Epsilon, the electromotive force in the circuit, is equal to minus d phi by dt, the time derivative of the flux across the circuit, and this is equal to minus L di by dt. This is just by substituting the value of phi in terms of the current that is flowing in the circuit. And this is just from Faraday's law. And now we apply these concepts to evaluate the self-inductance of a long solenoid. Now, what is a long solenoid? A long solenoid looks like this. We have a number of turns, and we have, if we consider that the total length of the solenoid is L, and the radius of each turn or each loop in the solenoid is equal to capital R. So when current flows in the loop, it is assumed that it is flowing this way, that is shown in the figure, entering the solenoid from this end and leaving the solenoid from this end, and it will introduce a magnetic field everywhere in space in general, and definitely it will introduce a magnetic induction between inside the solenoid as shown, and this will introduce flux that is passing through each one of these turns of the solenoid. And if we can evaluate this flux and divide this flux by the current that is flowing in the solenoid, then this way we can evaluate the self-inductance of this element, the solenoid. Keep in mind that the length of the solenoid is cursive L, and the total number of if the total number of turns is equal to capital N, then small n is the number of turns per unit length of the solenoid, which is simply capital N divided by cursive L, by the length. And the area of each turn is simply pi times capital R square. Keep that in mind. And now we look at the solenoid, at a cross-section of the solenoid. It looks like this. And this is an Amperian path. We use Ampere's law to evaluate the magnetic field. And we take an Amperian path like this. We ignore, first of all, the edge effects, the fringing at the edges of the solenoid. We ignore it, and we consider an ideal long solenoid where the fringes at the edges is ignored. And we can argue that the magnetic field outside the solenoid is zero. That means across this length, across CB, the magnetic field is zero. Actually, this can be derived by taking an Amperian loop that encloses all the solenoid, all this cross section of the solenoid. So if we apply Ampere's law, B dot dl along all of this Amperian path, hypothetical, it's not shown here in this figure, But if we can take B dot dl, this will be equals to 0 because the total current is equal to 0. There is current that's flowing out of the loop here in this from the upper part of the solenoid, the cross section of the solenoid, and then current, the same current is flowing into the loop area in the bottom part of the solenoid. So the total current that is crossing this loop that encloses all the solenoid is equal to 0. That means B dot dl should equal to 0. And in general, since this loop can be taken, the length of the loop can be taken anywhere. So if we assume that the magnetic field here is B1 and the magnetic field here is B2, so we have B1 minus B2 times the length of this Amperian loop, and that's equal to 0. And since B1 and B2 are in general not equal, because we can take this Amperian path anywhere we want, the length of the Amperian, this edge of the Amperian path, we can take it anywhere we want at any distance from the loop, from the solenoid. So B2 and B1 outside the loop, the solenoid outside, in the outside region from above and below. In general, B2 and B1 are not equal, and the only solution that B2 minus B1 is equal to 0 for general B1 and B2 is that if B1 itself is 0 and B2 is itself is 0, that means B outside the solenoid is equal to 0, and this is correct for an ideal long solenoid. This condition is true for an ideal long solenoid. So B outside is 0, and B in the edges also, AB and CD is 0. B, AB, and CD is 0. And this can be also shown that if we take the magnetic field of each introduced by each line, so in one line the magnetic field, it goes down, and between these windings and the field coming from the next winding, it's going up. So the field is cancelled between the windings. And also we can argue that CD and BA can be taken as short as we would like, which gives the contribution of the integral B dot dl along AB and along CD is equal to 0. Identically. So with these in mind, Ampere's law applied to this loop will be having only contribution from this length AD, which is inside the windings. So B dot dl across all the loop will have 0 contribution along AB, will have 0 contribution along BC, 0 contribution along CD, and non-zero contribution along AD, and this will give us the magnetic field inside the solenoid. And here the I is the current that is enclosed inside the Amperian loop, and if the current inside in each one winding is known, we can calculate the total current enclosed in the Amperian loop. So this can be done this way: B times H, where H is this length, A times D. This is the evaluation of B dot dl along this line, and the other contributions are zeros, as we said. This is equal to mu naught times I. What is I? I enclosed in this Amperian loop. I is equal to the number of turns per unit length times the length itself, so that gives all of the number of these turns inside the loop, times the current I in each loop, because in each one winding, the current that is flowing is equal to capital I. So we multiply by the total number of the windings inside this loop, this Amperian loop, and we get the total current. So this is the result, and the magnetic field inside the solenoid is accordingly equal to mu naught times N times capital I, where capital I is the current flowing through the solenoid, and small n is the number of turns or windings of the solenoid per unit length of its length. As we mentioned, this is the definition of small n, which is characteristic for the solenoid. And now the flux through one turn of the solenoid is simply, now we have evaluated the magnetic field, and we assume that the magnetic field inside the solenoid is uniform, like a uniform field, and we multiply this field mu naught small n times capital I. This is the field. We assume that it's uniform inside the solenoid. This is true for an ideal solenoid, times the area of the winding of the one loop of the solenoid. That's equal to the flux in one turn, through one turn. And but we have, in order to calculate the self-inductance of the solenoid, that's equal to the total flux divided by I. And the total flux is equal to the flux in one turn times the number of turns, the total number of turns of the solenoid. The total number of turns of the solenoid is equal to the density of windings or of turns, the number of turns per unit length, times the total length L, cursive L, of the solenoid. So N cursive L times phi is equal to the total flux through the solenoid divided by the current that is flowing in the solenoid. That gives the self-inductance of the solenoid as we see. And this involves a geometrical factor that is characteristic of the solenoid. It involves the length of the solenoid. It involves the number of turns per unit length of the solenoid, which are characteristic of the solenoid itself. So we can define the inductance from this result. We can define the inductance per unit length of the solenoid, because this is a characteristic property of the solenoid itself. And this L divided by cursive L, this quantity is the self-inductance per unit length, is equal to, we now substitute for the value of phi from the above equation, and this is equal to mu naught times n square times the area of the winding, or the area of the cross-sectional area of the solenoid, pi times capital R square. So this is an example of how to calculate the self-inductance of some loop or circuit, electrical circuit carrying current. And now we take into consideration another example. We take the toroid, and we calculate the self-inductance of a toroid. The toroid looks like this. It's just like the solenoid, but it's not straight. The windings are around some sort of a tire or so. So this is a toroid where the current enters from one end and emerges, goes around in the windings, and then emerges from the other end. And now the cross-section of the toroid looks like this, where we assume that the current is coming out of the page in the lower part here, and the current is going into the page in the wires on the top of the toroid. And now we use Ampere's law to calculate the magnetic field inside the toroid between the windings, as we did for the solenoid. We assume that the inner radius of the toroid is A, small a, and the outer radius of the toroid is B, and we take an Amperian path with radius small r between inside the windings, between the turns, that is in this region, and this is the Amperian path, and we can apply Ampere's law to evaluate the magnetic field. Remember that if we can look at the magnetic field introduced by each one of the windings, for example, here the magnetic field is this way, to the left directed, and from this winding, the next winding, it's this way too. From this winding, it's this way too. So we can imagine that the magnetic field goes along this Amperian path in terms of direction. And thus Ampere's law applied to this problem. We say that B, which is constant due to symmetry of the problem, which is constant along this Amperian path, times the length of the Amperian path, B times 2 pi r. This is coming from B dot dl along this Amperian path. It's simply B times the length of the path, which is 2 pi r, and that is equal to the total current enclosed in this. The total current is the current that is coming out of the page from each one of the windings. The total number of the windings in the toroid is assumed to be capital N, and the current that the toroid carries is capital I. So mu naught times N times I is the total amount of current that is flowing through, or that is enclosed by the Amperian path. And this gives a result. If N is the total number, B is equal to mu naught times capital N times I divided by 2 pi r. Now this is the magnetic field inside the toroid, and this magnetic field crosses each one of the windings of the toroid, of the loops, introducing a flux. So if we can calculate the flux through one loop and multiply it by capital N, which is the number of turns in the toroid, that will provide us with the total flux through the loops of the toroid, from which, of course, we can calculate the self-inductance. And this, now we assume ideal case where R, that is the radius, the average radius of the toroid itself, is much larger than the difference between the outer radius and the inner radius of the toroid. That means the toroid is really thin with respect to its average radius. And in this case, the magnetic field is uniform, can be assumed uniform, and inside the toroid. And the total flux linkage across the windings of the toroid is simply capital N, which is the number of windings, times phi, which is the flux through one of the loops, and this is simply mu naught times N square times I times the area of each winding over 2 pi r. Here we have to distinguish between r, small r here, which is the radius of the toroid itself, and the area here would involve a radius which is the radius of the loop or the winding around the toroid. So these are two different parameters that we should keep in mind. And the self-inductance of the toroid is thus L is equal to this quantity divided by I. So it is mu naught N square over 2 pi r times the area of the winding of the toroid. Of course, this is if the magnetic field is uniform across the winding. But in general, if the magnetic field inside the toroid in the windings, if the magnetic field is not uniform, then the magnetic field is calculated at each position. Of course, it's a function of r, as we noticed in the previous formula that we have evaluated. and we can integrate over the area of the winding itself, and this will give us an accurate calculation, or a more accurate calculation of the flux through the windings, and that will give us a more accurate calculation of the self-inductance of the toroid. And now this is all related to the self-inductance, which is the geometrical factor that is correlating the flux linkage in a circuit with its own current. But now we come to the question of what is the relation between the flux linkage in a circuit and between the currents in other circuits, or in a second circuit, for example, if two circuits are interacting with each other, and that gives us the mutual inductance. And we consider this figure the flux linking circuit A due to current in circuit B. This is circuit B. There is current in circuit B, and we assume that the current is varying, so that the flux is varying. In general, it's an AC case, in general. And the flux linking A, circuit A, is given by B, the magnetic field due to circuit B in an element of area of the circuit A. We take element of area DSA, we figure out what is the magnetic induction due to circuit B in that little area. B dot DSA is the flux through that element of surface area DSA of circuit A, and integrated over all circuit A, that will give us the total flux through circuit A due to circuit B. And this can be rewritten in terms of the vector potential, as curl A, the vector potential due to the current in B, dot DSA, that is integrated over the surface area of the circuit A. This is the flux in A due to circuit B. And this flux, accordingly, we can use Stokes' theorem to convert this surface integral into a contour integral, and this gives phi equals, instead of curl A dot ds, it is simply A dot dl. So A arising from the current distribution in circuit B dot dl, the element area in circuit A, and this is integrated over the circuit A, circuit A. This is the flux linkage in A through A due to circuit B. And thus, we can rewrite now the value of the vector potential due to circuit B as we can substitute for it by its value, and this gives phi is equal to integral over the circuit A of the vector potential due to B, which is mu naught IB over 4 pi times DLB divided by R, dot DLA, where R is the distance between the element DLB and the element DLA. And this can be rewritten as a factor, a geometrical factor, multiplied by the current IB. So the flux through circuit A is equal to IB, the current in a second circuit, IB, times some factor. And that factor, MAB, it's called MAB, which involves geometrical factor of the two circuits together, as we notice. And this leads to a Newman equation, which states that the mutual inductance of two circuits is simply equals to mu naught over 4 pi times integral over circuit 1 over the first circuit, integral over the second circuit of the element of length in the second circuit dot element of length in the first circuit divided by the distance between these two elements. This is a geometrical factor, as we noticed, that depends on the geometry of both circuits interacting, and symmetry with respect to integration. We can do the integration either way, and there's symmetry, complete symmetry with respect to integration. The symmetry leads to the conclusion that MAB is equal to MBA. That means this geometrical factor, if we consider the flux linkage in A due to B, is exactly the same as if we consider the flux linkage in B due to A. We reach exactly the same result. The electromotive force induced in circuit A due to a change in the current in circuit B is thus, the electromotive force is epsilon is equal to minus d phi by dt, which is equal to minus m ab di by dt. Now we consider two coaxial solenoids, and these two coaxial solenoids, they are like two circuits that are interacting with each other. So, and we calculate the mutual inductance for these two coaxial solenoids. And as we have mentioned a little while ago, whether we calculate MAB or MBA is the same, and thus the flux in A due to current in B is simply mu naught times small n B times IB, that's the induction due to B, times the windings, the number of windings in the solenoid A, which is small n A, times the length of solenoid A, times the area, and that gives the flux. It's the magnetic field times the number of turns times the area. And thus, the mutual inductance of the system is equal to this flux divided by IB. So this is the flux through A divided by IB is equal to MAB, mu naught pi r A squared times NB times NA times the length of solenoid A. And that can give us a result of, we can obtain the mutual inductance per unit length, actually, if we divide by LA, scarcity LA. And now we move to calculate the energy of a magnetic field, the energy in a magnetic field, just like the way we did when we considered the energy stored in an electric field. We consider this problem now. And here we have a circuit which contains an electromotive force epsilon that drives current in this circuit, and we have a resistor R, and we have an inductor L with inductance, with self-inductance L. And when we apply Kirchhoff's law to this circuit, we obtain the electromotive force epsilon is equal to IR, the voltage drop across the resistor R, plus the voltage drop across the inductor L, which is simply L times di by dt. And thus, if we multiply the equation all through by I, the current I, we obtain I times epsilon, which has dimensions of power, which is energy per unit time. And this is equal to I squared R times plus L times I times di by dt. It's just multiplying by I. And we notice that the first term, which is I squared R, is the right, on the right-hand side of this equation, is the rate at which energy appears as Joule heating. It's heating in the resistance. It's the Joule effect. And if this is the total power delivered to the circuit by the electromotive force, part of this power appears as heating, so that the rest of the power, due to conservation of energy, must be stored in the inductor in terms of Li di by dt. So this is a conclusion. So by energy conservation, the second term should represent energy stored in the inductor. But how does it store the energy in the inductor? It stores it in terms of energy in the magnetic field, because the inductor has a magnetic field as the current goes in. And thus dUB by dt, its power, dUB by dt, the rate of change of the magnetic energy that is stored in the inductor, is simply the self-inductance L times I times di by dt. And we can integrate this in order to obtain the total energy stored in the inductor, dUB, which is evaluated from 0 to the maximum, to the final point at which the current that is flowing is I. The energy is UB, and that is integrated, that is equal to the integral from 0 to I of Li di. This is just a consequence of this equation. And thus the magnetic energy is equal, UB is equal to 1/2 L times I squared. This is the magnetic energy in the inductor. And if we would like to see how it looks like in terms of the magnetic induction, just like the way we did in the case of the electrostatics. And here, in order to see this, we consider a long solenoid, and the energy per unit volume in the long solenoid, in general, this is equal to UB divided by the area of the solenoid times the length of the solenoid, which is the self-inductance times I squared divided by 2 times the volume of the solenoid. That is the density, the energy density per unit volume. And now we substitute for the self-inductance of the solenoid, and this gives UB is equal to 1/2 mu naught n squared I squared. And now if we introduce instead of I, the current I, if we substitute in terms of B is equal to mu naught Ni, so instead of I we use B in this relation, and we get UB is equal to 1/2 B squared over mu naught. So it's proportional to B squared, and this is exactly similar to the case of electrostatics, where we remember that we remind ourselves that it's 1/2 epsilon naught times E squared. And at this point, I finish the lecture, and I thank you for your attention.